All right. So after the sacrifice 8, this is going to be our first lecture, and it's also going to be the last for this week because uh, we have skipped the Monday class. So this is Tuesday class, and we are just going to cover one more chapter today. And for the last weeks of our summer term, we will be remaining 3 chapters to cover. And here we are going to talk about evaluating a single project. And we are just going to perform present word, future word, and annual word analysis. We are basically going to use the compounding equations and the extended notation that we have learned so far in order to determine the present word or the future word of alternative investments, alternative project. And at 3 steps, we are going to complete today's lecture. Okay, so when we perform applications on the present word method, we are also going to learn a special case of the present word method, which is called the capitalized word method. So this one is a special case of the present word analysis. Then we are going to perform a future word methodology, and finally the annual word methodology. And again, a special case of the annual word methodology is the capital recovery cost calculation. We are going to learn all about those and finalize today's lecture. So let's move forward. So it says when companies need to decide between different alternative implementation plans of a project, they need to consider the initial costs occurring at time 0 and the future positive or negative cash flows to decide which alternative returns the highest return. Now, I'm just going to explain that sentence with a simple example. Imagine now you are going to purchase a printer, okay? Now, the initial costs of these printers may differ from brand to brand, okay? So there are several brands of printers, for example, Canon, Xerox, and HP, and we can just count the names of many different brands of printers, okay? And even if these printers perform with the same performance, even if they have the same speed and quality of print, their price may differ from each other, may be different from each other. So why these prices are different from each other? Why the initial costs are different from each other? Because if the initial costs are less, then you are supposed to, when you are using these printers, you are supposed to use the supplementary materials of that printer in the future. For example, you are going to purchase the ink of that printer, right? So if the initial cost is low, then usually the cost of the supplementary materials in the future are going to be high. If the initial cost is larger, then the supplementary material cost that you are going to use in the future is going to be low. So because of that reason, when we want to compare alternative printers to purchase, it is not a very good idea to compare them by looking at their initial costs only. Remember now, in the future, they are going to create future costs based on the ink usage, etc. Okay, so just like that, if we implement a project, there may be several different plans of implementing project, each involved with a different initial cost that we need to pay right now. But in each plan, the time and the amounts of the future costs and the timing and the amounts of the future positive cash flows, revenues, are going to be different from each other. Now, we need to select the implementation alternative of this project, which gives us best performance. And in order to make a performance comparison of these alternative project plans with alternative cash flow diagram, we need to compare them at a certain interest rate, and we need to compare their either present worth or future worth or annual worth. Okay, we can use either one of these methodologies. At this point of lecture, there will be no difference between these methodologies. However, I'm just going to emphasize the differences of these methodologies in the future chapters. Okay. So the cash flows in total are called the capital investment of the alternative plan, and we are going to use these methodologies for each alternative. However, at this point, all these analysis methods, all these three analysis methods should result with the same decision. Okay. Now, under a certain interest rate that we assume, if the present worth method tells us to choose the plan A over plan B, if you use the annual word method or the future word method, again, on the same interest rate, these two methodologies are to make you choose plan A or plan B in any way. Okay. So we are going to start from the present word method. And what does the present word method do? Now, the present worth of a given series of cash flows is the equivalent value of the cash flows at time zero. Now, in every project, when we list the alternative investment plans, in each investment plan, in each implementation plan, we are going to see some initial costs plus future revenues and future costs, which occur at periodic time points. Now, our objective here in the present worth method is to calculate the present equivalent value of all future cash flows at time zero, and we are going to subtract the initial cost from that, and that is going to be the present. Now, under which interest rate we are going to compute the present. So if we assume a discrete periodic compounding with constant periodic effective minimum attractive rate of return, then we are going to use that minimum attractive rate of return to calculate the present worth of these values. Now, let's just say the inflow is cash flow zero, which is usually negative. Plus, let's just say in the end of the first period, we have a cash flow 1. It can be either positive or negative, depending on the costs and the revenues on that time point. We are going to discount that end of period 1 cash flow by single payment present worth factor P over F, multiplying it with the single payment present worth factor under I% interest rate, which is our periodic effective minimum attractive rate of return for one period. We are going to do the same for the second end of the period cash flow, but this time we are going to discount it with single payment present worth factor under I% interest rate for 2 periods, so on and so forth. For all end period payments, end of period cash flows, we are going to discount them with single payment present worth factor under I% effective periodic minimum attractive rate of return and for end periods. Now, if you have studied last week, you know the definition of the minimum attractive rate of return. So why do we use in our analysis? Every organization has a minimum attractive rate of return to evaluate their investments, and they need to compare alternative project plans with alternative cash flow structures, again under this minimum attractive rate of return. So in this notation, EFK is the cash flow at the end of period K. Sometimes it can be positive, which means at that period, the revenues are going to be greater than the expenses, or sometimes the cash flow at K, time point K, can be negative, which means at period K, the costs are larger than revenues. Okay. Here, N is the total lifetime of the project. So of this project, the future cash flows are going to end in the end of period N. Now, so we need to determine for how many periods the project will cause these cash flows. And some projects may return cash flows forever as well. So there may be some projects, for example, if you think about the third bridge, Yavuz Sultan Selim Bridge in Istanbul, so this project is going to return cash flows forever, right? So once you build this bridge, you are going to use that bridge for a very, very long amount of time, maybe 200, 300 years, okay? So when you are going to evaluate these projects, you need to remember now they are going to return cash flows for a very, very long amount of time, assuming almost forever. Now here, the single payment present worth factor, P over F, under I% interest rate for K periods is formulated as 1 plus I to the power minus K. Now, even though we simplify the present worth factor by discounting each cash flow at the end of each period one by one with a single payment present worth factor, in practice, some of these cash flows are going to form a uniform series, and some of them are going to form a gradient geometric series. And in that case, we are just going to use easier methodologies to discount all future cash flows with a single step. Now, in this question, we are going to see I'm sorry, the connection problem right now, so I'm just going to change a connection point. I think you cannot see the presentation file at the moment. Enable another connection point. Okay, I have reloaded the session. Now I am just going to share my screen once again. So this is the point where we have that. I was just showing you and making comments on the present word methodology based on the equation that I have shown you. And now we are going to practice the same methodology to evaluate the present word of a investment plan. Now, in this question, it says a piece of new equipment has been proposed by engineers to increase the productivity of a certain manual welding operation. Okay, so welding means what? Welding means kaynak. Kaynak. So this is a manual welding operation, and we want to increase the productivity of this manual welding operation. And this new equipment is going to help us. However, if we want to purchase this new equipment, the investment cost that we need to pay at the moment is going to be $25,000, and the equipment will have a market value of $5,000 at the end of the study period of 5 years. So what does that mean? If you purchase this equipment right now, you need to pay $25,000. However, in 5 years, if you want to sell this equipment in the end of 5 years, you will be able to sell it from $5,000. So the market value at that time is going to reduce to $5,000. By the way, it is going to be a second-hand equipment in any way. So at the end of a study period of 5 years, you are going to be able to sell it from $5,000. So this $25,000 is a cost, initial cost that you need to pay in the beginning, and this $5,000 is a revenue, is a value that you are going to be able to get in the end of 5 years. Now, increased productivity attributable to the equipment will amount to $8,000 per year after extra operating costs has been subtracted from the revenue generated by the additional production. So it says for 5 years, for the following 5 years, in the end of every year, you are going to get a net $8,000 of revenue by increasing the productivity by this equipment. However, there will also be some operational costs in the end of each year related to this equipment, but this $8,000 is the net profit. It is the net profit. So revenues minus in each year, the revenues minus expenses is going to bring $8,000 of positive cash flow. The question is this: we want to use present worth method and calculate the present worth of this cash flow diagram. What is the present worth of this investment? However, in the first part, it says the firm's minimum attractive rate of return is 20% per year compounded annually. In that case, is this proposal a sound one? So basically asking this, under this minimum attractive rate of return of 20%, would you invest in this equipment? Because you see, this equipment is going to cost us $25,000 right now. For 5 years, it is going to bring $8,000 in the end of every year and additional $5,000 in the end of the 5th year. But I mean, you know, these amounts are going to be collected later, not right now. So under 20%, so if the company is aiming for at least a 20% rate of return in each year, which compounds annually, would it be worth to invest in such a new equipment, it says. Secondly, in part B, the question says that if the minimum attractive rate of return is again 20% per year, but it is compounding continuously instead of annual compounding, if the organization, if the company assumes a continuously compounding minimum attractive rate of return, now asking the same question, is this proposal a sound one? Now we are going to answer both. Now this is the cash flow diagram of our investments. And in the beginning, we need to pay $25,000. Right now, we have a negative cash flow. In the end of every year, we have an $8,000 of positive cash flow as the net profit. And in the end of the 5th year, we also have a second-hand market value of the equipment. When we want to sell it again, we are going to get an additional $5,000. Now, you see, the assumed minimum attractive rate of return is 20% per year. So we would like to calculate the present worth of these cash flows. How do we do that? Now, first of all, the positive cash flows are positive and the negative cash flows are assumed negative. So the present worth of this uniform series of $8,000 will be obtained by multiplying $8,000 with uniform series present worth factor, which is P over A, under 20% interest rate for 5 years. And final $5,000 here is going to be discounted to the present worth by multiplying it with the single payment present worth factor under 20% interest rate for 5 years. And finally, we have a negative $25,000 here. However, because it is occurring at time 0, we do not multiply it with anything. We simply take it as negative $25,000 because it is already an amount that is paid in the present. Now, for P over A and P over F, we can check these values from our compounding factor tables, the first table that we use. Now, for that, for P over A, we need to check A over P, which is the capital recovery factor. For capital recovery factor under 20% interest rate for 5 years is 0.33438, but the uniform series present factor is the multiplicative inverse of it. Similarly, we do not have P over F's on our tables. We have F over P's. The F over P value under 20% interest rate for 5 years is 2.4883, and the multiplicative inverse of it is calculated. And the present worth of this investment is $934.28. Now, under the minimum attractive rate of return of 20%, which compounds annually, the present worth under this minimum attractive rate of return is greater than or equal to 0, which is $934. So economically, we have an economically justifiable investment here. So we can basically purchase this equipment because it is going to bring us more than 20% in each year compounded annually, because the present worth is positive. Now, in the second part, we are just going to assume the minimum attractive rate of return of the company is again 20%. However, it compounds continuously. In that case, we calculate the present worth, but to remember continuous compounding, we are going to use square brackets instead of ordinary brackets here. So under continuous compounding of 20% interest rate per year, the present worth will be calculated again by multiplying the uniform series with uniform series present worth factor under 20% interest rate for 5 years, but continuous compounding. Remember, when we have continuous compounding, we are always using square brackets. Again, the final $5,000, which is paid in the end of the fifth year, is going to be multiplied with single payment present worth factor under 20% interest rate for 5 years. And we again subtract $25,000 from that. Now, this time we need to check our second table. So discrete payments, but continuous compounding. Under continuous compounding, but discrete payments, the P over A and P over F values are going to be computed with A over P and F over P values, and we take the multiplicative inverse of them. And the calculation will give us a minus $319.79. And you see the present worth under these continuously compounding interest rate or minimum attractive rate of return, the present worth is calculated negative. So this means if we assume a continuous compounding minimum attractive rate of return of 20%, then this investment is not economically justifiable, so we should not purchase that equipment, it says. Okay, so it all depends on the minimum attractive rate of return percentage and the compounding assumption of the organization. So we need to perform all these present worth analyses based on the minimum attractive rate of return and the compounding periods of that minimum attractive rate of return of that company. And for part A and part B, as you can see, we have different results. Now we are going to solve another question related to the present worth method. We have a retrofitted space heating system, and it is being considered for an office building. Okay. The system can be purchased for $110,000, and it will save an estimated 300,000 kilowatt hours of electric power each year over a 6-year period. Now it says the initial investment cost will be $110,000. And every year it is going to make a saving of 300,000 kilowatt hours of electric power. And the kilowatt hour of electricity costs 10 cents. The kilowatt hour of electricity costs 10 cents, and the company uses an effective minimum attractive rate of return of 15% per year in its economic evaluations of refurbished systems. Now, the initial investment cost is very large. However, every year that it is used for 6 years, at every year we are going to make 300,000 kilowatt hours of savings. Each kilowatt hour is introducing a 10 cent of saving to us. Okay. Now the effective minimum attractive rate of return is 15% per year. And the market value of the system will be $8,000 at the end of 6 years. So in the end of the 6th year, if we want to sell this space heating system, though we purchase it from a very, very large amount, like $110,000, we can sell it from $8,000. Okay. The operating and the maintenance expenses are negligible, it says. So usage, when we use this heating system, we are, of course, going to have some operating and maintenance expenses as well, but it says, the question says that these values are so small, so they should not be a part of our analysis. So we are going to use the present worth method to determine whether this system should be installed or not. However, again, we are going to have two parts, two assumptions. In the first assumption, we will assume that this 15% per year minimum attractive rate of return is going to be annually compounding, and the annual savings occur at the end of the years. So for example, if in a year 300,000 kilowatt hours of energy power has been saved, and each kilowatt hour saves 10 cents to us, so in the end of the year, in part A, we assume that in the end of the year, $30,000 of savings will occur. So by using this heating system, we are going to save $30,000 in the end of every year. Now, in part B, it says we are going to assume continuous compounding, just like in the previous question. We are going to assume a continuous compounding, and the annual savings occur continuously over the year. Now, it says this 300,000 kilowatt hours is going to be saved, not in the end of the year, but these savings are going to occur uniformly over 1 year. Okay, at every second, at every minute, we are going to save some energy. Okay, therefore, these savings are not going to occur in the end of the year. So this $30,000 of saving is going to occur continuously over 1 year. So in this case, the payments are continuous. The payments are continuous. Actually, we have studied this topic in chapter, I guess, 6. It should be chapter 6. If you refer yourselves to chapter 6, you will see there the continuous payments, how we deal with the continuous compounding and continuous payments. So we are going to look at these two solutions separately. Now, the question says the yearly effective minimum attractive rate of return is 15%. And in the first part, we assume that the payments are made in the end of the years. Initially, we will have a cost of $110,000 plus in the end of, so because this is a cost, this is negative. In the end of every year, we will have $30,000 of savings in the end of every year, and it is going to occur for 6 years under 15% effective minimum attractive rate of return. We need to calculate the present worth of this $30,000 by multiplying it with the uniform series present worth factor under 15% minimum attractive rate of return, and for 6 years. Finally, in the end of the 6th year, if we want to sell this heating system, it sells from $8,000. So these $8,000 of profit must be discounted to present value by multiplying it with the single payment present worth factor under 15% interest rate for 6 years. Now, again, these values are going to be checked from discrete periodic compounding, discrete payments and discrete periodic compounding or annual compounding table. So we need to check the A over P, the single payment capital, uniform says capital recovery factor, and F over P, single payment compound amount factor. We are going to look at these values and take the inverse of them to identify these compounding factors, and the result will be approximately $7,000 approximately. Okay, so that is the present worth of this investment under 15% annual effective minimum attractive rate of return that compounds annually. Now for part B, we assume that the annual savings of these $30,000, first of all, in part B, we assume a continuous compounding. So when we want to calculate the present worth under 15% effective minimum attractive rate of return, we need to assume a continuous compounding, so we need to use the square brackets instead of ordinary brackets. Now, again, we have the same cash flow structure, the initial costs and the periodic savings, $30,000, and in the end of the 6 years, the market value of the heating system are going to be the same as before. However, the only difference here is this. Actually, there are two differences. Because of the continuous compounding, you need to use a square brackets instead of ordinary brackets. And we know that this $30,000 savings are not going to occur in the end of the periods, but they are going to occur continuously over 1 year. Okay, so in the end of the 1 year, the total saving will be $30,000, but every day, for example, if the company works for 360 days, every day we are going to save $30,000 divided by 360. We are going to save that much amount of energy on every day, or every second, every minute we are going to make some savings, but the amount of savings throughout the year is going to stay the same. Okay, so that is, this $30,000 is not the end of year payment, but instead it is the average rate of savings per year. So on the average, we save $30,000 every year, but at a constant rate. Therefore, we need to multiply that with a uniform series present worth factor under continuous payment. So for continuous payments, we use P over A bar. Remember, A bar is the continuous payment, annual continuous payment rate. And these two values, this second value here is going to be checked from table 3, and the third value here is going to be checked from table 2. So that is going to be checked from discrete payment but continuous compounding table, and that is going to be checked from continuous compounding and continuous payments table, the third table and the second table. And in that case, the present worth is going to be even larger. Why? Because the savings are not going to occur at the end of the years, but they are going to occur throughout the year. Therefore, these savings are going to gain much more interest, under 15%. And because of that reason, the present worth is going to be larger than 6,991. So this is how we solve this question. Now we are going to solve one more question, and after that question, we can give a break. Stan Moneymaker has the opportunity to purchase a certain United States Treasury bond that matures in 8 years and has a face value of $10,000. Now remember, when we talked about bonds, we pay some initial amount to purchase these bonds, and we need to keep these bonds until the maturity date. So that is the total period of the maturity period of the bond, and that is 8 years. So Stan Moneymaker needs to wait for 8 years, and in the end of 8 years, when he returns the bond to the market, he is going to take $10,000. Okay, so $10,000 is going to be the final payment, the terminal payment that is going to be made for this bond if you wait for 8 years. The bond pays dividend to the bondholder every 3 months at amounts of 2% on the face value. So what is the 2% of the face value? 2% of the face value is $200. 2% of the face value is $200. So this means what? In the end of every 3 months for 8 years, in the end of every 3 months, a 2% face value, which is $200, is going to be paid to Stan Moneymaker as well. So Stan Moneymaker is going to purchase this bond for 8 years. In the end of every 3 months, he is going to get $200. And in the end of 8 years, he is going to get $10,000. Stan would like to earn 12% nominal interest rate, which compounds quarterly. Okay, so the nominal interest rate is 12% from that bond. That is the yearly interest rate, but it is not the yearly effective interest rate. It is the nominal interest, and it says it is compounding quarterly. Therefore, the effective quarterly interest rate is going to be 12%, 12 divided by 4. It is going to be 3% per quarter. So this is the amount of money that he wants to earn this bond. Because the interest rates in the economy have risen since the bond was issued, how much should Stan be willing to pay for the bond? So at what is the fair market value under this nominal interest rate of 12% that compounds quarterly? What is the fair market value of this $10,000 bond? Now, first of all, The nominal interest rate is 0.12, and the quarterly effective minimum attractive rate of return is 0.03, which is 4 divided by the nominal interest rate. So this is going to be the interest rate that we are going to assume. Now, how many periods do we have in this problem? Actually, the bond has a maturity date of 8 years. However, because we have dividends to be paid in the end of every 3 months, we totally have 32 periods. Each period consists of 3 months. For 32 months, we are going to get $200, which is 2% of the face value in the end of every 3 months. And we have a uniform series here. Now let me show you the cash flow diagram. The cash flow diagram here. The cash flow diagram has a shape like this. So we have 1, 2 here, 3 here. So I'm not going to write all of them like this. We have 31 and we have 32. So if you purchase this bond, the STEM moneymaker is going to purchase this bond right now. He is going to get $200 in the end of every 3 months for 32 quarters, which is 8 years. And in the end, he's going to take a total of $10,000 as well. Okay. So in the end of every 3 months, he's going to get $200,000. But in the end of the 32nd quarter, he's going to get a $10,000. So we would like to calculate the present value of these future cash flows under a nominal interest rate of 12%, which has an effective interest rate, introduces an effective interest rate or effective minimum attractive rate of return of 3% per quarter. So we need to multiply $200 with the uniform series present worth factor under 3% effective periodic interest rate for 32 periods. And this $10,000 will be multiplied with single payment present worth factor under 3% effective interest rate for 32 periods. Again, these two values can be checked from the compounding factors table, the first table, and that present value will be $7,959.90. So this means what? If the nominal minimum attractive rate of return of STEM moneymaker is 12%, which compounds quarterly, then the fair market price of the bond is $7,959.90. That is the maximum amount that Stan should pay if he wants to get a 12% nominal minimum attractive rate of return that compounds quarterly. If he pays more than this amount to that bond, in that case, he's going to experience a less rate of return from that investment. Okay, so that is the maximum amount that he will be willing to pay for that bond. All right, so before skipping to question 4 here, okay, so it is going to be a little complicated this time. So before skipping the question 4 here, let's just give a break of 10 minutes. After 10 minutes, we are going to meet again and we are going to continue with the second part of this chapter.